So hi, my name is Kinetical Quali, and this is StormCartographer. So StormCartographer is an autonomous Jovian navigation system that utilizes a variable altitude buoyancy drone to navigate Jupiter's giant red spot. So for my navigation scenario, the challenge for this scenario was that, as I said, it takes place on Jupiter, so specifically the giant red spot, which means that there is no GPS enabled, and as Jupiter is a gas giant with no surface, there are no landmarks. The drone also needs to be fully autonomous, mainly because the communication latency between Jupiter and Earth takes around 54 minutes for a one-way signal. So for my navigation pipeline, it's broken down into two main tracks. The first track being the vertical track. This deals with the buoyancy controller, and this operates in the Z-axis only, and it has no thrust. It has no thrust because the drone modulates the density of a lifting gas to ascend or descend passively. This is directly inspired from a submarine ballast system, where compressing the gas container increases the density and the drone descends, and expanding this container decreases the density and causes it to rise. For my horizontal track, it utilizes four ducted propellers that will push against Jupiter's atmosphere. It also takes into consideration a raycast sensor, the potential field, and the PID controller, which all operate at the horizontal plane, so the X and Y, but the raycast sensor looks at the X and Y at the current position, the current Z position. After this, both tracks then feed into a shared sensing stage, which comprises of an IMU dead reckoning and an optical flow. In order to mitigate any sensor errors and any drift, I've also incorporated sensor fusion as my state estimation, which looks at the X, Y, and Z axes. So, looking at my algorithms, firstly at the buoyancy altitude control, as I said, it only takes place on the Z-axis, which means there's no PID and there's no thrust. I have a damping coefficient of 0.85, which is visible in the code here as the Z velocity, and this has been used to smooth any the ascent or descent of the drone. But why use this buoyancy altitude control over a regular propeller system? Well, as it takes place on Jupiter, the solar constraints are 27 times weaker than that on Earth, so having a continuous vertical thrust using propellers is just unsustainable. But the downsides of having this buoyancy altitude control is that it is quite slow, with a max vertical speed of 0.4 meters per second. For my raycast sensor, which we'll take a closer look at in a moment, but I have 12 rays that are positioned in the horizontal plane at 30-degree increments, and these are used to detect any obstacle directly in front or around the drone, but only in the horizontal axis. And because it only takes place in the horizontal axis, the limitation of this is that it cannot detect anything directly above or below it. So for my potential field, it operates in the X and Y axes only, and I have a scaled gain of 2.5, and I chose this algorithm over A star or Dijkstra's due to the fact that there'll be no map present, like no predetermined map present before the mission begins, whereas A star and Dijkstra's need this beforehand. For the IMU Dead Reckoning, I've added a Gaussian noise to the known accelerations. So in the horizontal plane, I've got 0.2 meters per second squared, and in the vertical plane, I've got 0.1 meters per second squared. But the issue with having this IMU Dead Reckoning is that as time goes on, drift increases, which means it must be corrected. So for my optical flow, I have the model has a downward facing camera that is used to observe cloud textures, but this only works in the horizontal velocity only. The algorithm I used was the Lucas-Canede, and I validated this using the static image pairs within MATLAB. The limitation of this, though, is that the cloud features do move with the storm, so this may introduce some errors where different levels of speed, wind speed, could affect how clouds move, which can lead to more errors. Lastly, I have my filter, my sensor fusion complementary filter, which essentially fuses the IMU and optical flow at each time step. So looking at the horizontal, the fused is 0.85 times the IMU plus 0.15 times the optical flow position, and the vertical uses that same 0.85 being the alpha value times the IMU plus 0.15 times the altitude correction. So for my PID controller, it operates exclusively in X and Y axes, and it takes desired heading from the potential field. It computes the velocity error and outputs the horizontal acceleration. And to do this, it uses the gains. So the first gain being the proportional, I have it at 3. The integral I have at 0.08, and the derivative I have at 0.6. So for my closed feedback loops, so I have 2 of them, and they both run simultaneously at 20 Hertz. Looking at the first one, the horizontal loop, it incorporates the raycast and the potential field in order to find the desired heading. This is then fed into a PID controller in order to determine the acceleration. For my vertical loop, any altitude error is then used as part of the target's vertical velocity, which is then used as part of the buoyancy damping, which smooths the command and allows the altitude to update, which is useful for the IMU because the IMU then estimates the Z position. This is all then fed back so that the 3D goal distance can be determined. So let's look at the simulation. So on the left I have my top-down view, and on the right I have my 3D view. Yep. So as you can see, it did avoid the obstacles. Yep. So I was quite happy with the performance. It did reach the goal state in just under 15 seconds, and it had a fusion improvement of around 30%, depending on when I ran the model. Sometimes it was 29.7, sometimes it was like 29.2, but generally around 30%. So for my my analysis of the algorithm, from the demonstration, it was quite clear that the drone moved very smoothly from the start position to the goal state, thanks to all the different algorithms included, specifically the PID, because it allowed for a smooth velocity and no overshoot. But there were some limitations. For example, the z-axis IMU, the drift for this was uncorrected, and as previously mentioned, I had the raycasts only in the horizontal plane, so objects directly below or above the robot, the drone, were not accounted for. And yes, optical flow, as I previously mentioned, it only assumes that there's a static background, which isn't the case inside Jupiter's giant red spot. And looking at the future improvements, there are a few, but the ones I would like to highlight the most is that I would like to fix the raycast situation by not just having it as in the horizontal plane, but I'd like to have it as a semi-spherical pattern. That way it can account for any vertical objects, or any objects in its vertical plane. I'd also like to add a barometric pressure sensor, which can be used to fix the z-axis IMU drift by constantly determining how high the drone is, by utilizing pressure. And thank you. Here are the links.